Picking back up with number 2, as we look at this double integral, we're going to notice that it's definitely a type 1 integral. As we see that we integrate with respect to y first, there's only one issue, there's one major concern. As we take our antiderivative of sine of y squared, we quickly realize that really we can't do that. So that's a big concern with being able to solve this problem. It is a type 1 region. Our x boundaries, of course, are going to be going between 0 and 1. And for our y, we have a upper bound of y equals 1, and then a lower bound of y equals x. And of course, as we look at this region then, as if we were integrating this, the problem of course, is in regard to taking our antiderivative. It begs the question, is it possible to rethink this problem through as a type 2, and we can look at this region as a type 2? Perhaps that will help. Indeed, it will. Let's see what we've got. We've got the sine of y squared. Now we'll integrate first with respect to x and then with y. So we see our upper boundary here would be x equals y. Our lower bound would be x equals 0. And then integrating, you look at the all of these horizontal lines run from y equals 0 all the way up to y equals 1. Would this be more approachable? Indeed it would, because I can take the antiderivative of sine of y squared with respect to x and get x sine of y squared. Use our fundamental theorem here, and plugging in our y, we get y of sine of y squared minus a 0 times the sine of y squared. Of course, that just goes away. As we're looking here at this integral, I'm going to rewrite it up here at the top. You might realize that even this antiderivative isn't readily recognizable, but we can do a u substitution. We can let u equal y squared. Du would be a 2y dy. Y dy actually is present in this integrand, and that y dy, if we solved for that, we'd get du all over 2. So we'll have a du all over 2. This would become a sine of u. Our bounds, wow, if we were to let y equal 0, u would equal 0. If we were to let y equal 1, u would equal 1. Amazingly, our boundaries are actually going to be the same. So we'll have 1/2 the integral from 0 to 1 of the sine of u du. Taking our antiderivative, we will get negative cosine of u evaluated between 1 and 0. If we pull that negative 1/2 out, we'll have the cosine of 1 minus the cosine of 0. Cosine of 1, we don't know what that is. However, the cosine of 0 is actually a 1. Now we can distribute that negative in and change our boundaries around here. This would become a negative cosine of 1 and a plus 1. Then divide by 2. That might be the nicest, easiest way to write the problem out. One final part of the lesson. There's an incredibly powerful property of integrals that says if we integrate the constant function of z equals 1 over a region D, we simply get the area of that region D. And that can really make some problems that we even saw last year in Calculus BC way, way simpler. And that's the end of our lesson.